So briefly about yeast. The yeast that's used by bakers is Saccharomyces cerevisiae. It is a single-cell organism that can live with or without oxygen. Now, with oxygen, it can metabolize foodstuffs like glucose to produce a large amount of energy. And without oxygen, it can still survive, but it can't produce as much energy. This has an important consequence. It takes a lot of energy for a yeast cell to make another yeast cell. The cell walls that have to be created take a very large amount of energy. And the amount of energy that is available to the yeast cell when it is in an anaerobic environment, that is an environment without oxygen, like it is when it is in a dough. When it is in an anaerobic environment, it cannot create enough energy to fund making more yeast cells. So the reproduction of yeast cells stops when the yeast cell doesn't have oxygen. Yep.
So this is equally as important if you're using commercial yeast or if you're actually baking with sourdoughs, or natural leavening, because the natural levains have got a combination of lactobacilli and wild yeasts, and these wild yeasts live by the same rules as basic, and some of them are in fact Saccharomyces, and not necessarily Cerevisiae. And so one of the practical outcomes of this understanding about the oxygenation and the fact that they only make more yeast cells if there's oxygen available is an instruction that, for example, if you're making a liquid starter, when you feed it, to actually make sure that you beat some air into the system. It's going to make sure that you keep your population of yeasts quite high, and as they're the main gassing power in a natural starter, then keeping the population of yeast high can be quite useful in terms of maximizing the value of that starter in terms of risen bread.
Thank you, Aaron. So salt. Salt has several actions. It works as an antioxidant, and Clavel recommends its addition at the beginning of the mixing process for that reason. It increases the cohesiveness of dough during mixing. Without salt, the dough will be more slack. Salt decreases the rate of fermentation, and it can be very, very dramatic as to how much it decreases that rate. So 4% salt will result in a 70% reduction in fermentation rate, which is very substantial. And that would be obviously a very large amount of salt and would give an adverse taste to the dough. But in lesser amounts, a baker can use this knowledge on a warm summer day, perhaps, to slow down the fermentation of the dough, if that would better fit the baker's schedule. And of course, salt makes a beneficial contribution to taste. All one has to do is go to Tuscany and taste Tuscan bread to recognize the benefits that salt provides. Mixing. So mixing is really, really important. It homogenizes the dough. It disperses the dry ingredients. It equalizes the absorption of liquids. It entraps air into the dough. And this is important in part for the reasons that Andrew mentioned, the benefit that oxygen provides. But it's also important in a very different way. It creates little tiny bubbles called gas nuclei, which I'll talk about more in just a couple of minutes. And it exposes dough to oxidation. Now this can have effects that are positive in that it can enhance the oxidation of the gluten-forming proteins, can enhance the formation of gluten, but it can also oxidize the carotenoids that give flavor to the bread and result in a loss of flavor. So initially, the doughs are not homogeneous. The absorption of water is not even. The first particles to get wet get more water than the last particles, and mixing provides a process by which the water gets equal and the dry materials are equally dispersed and everything's equally moistened. The mixing also is the process during which sugar that might be added to the dough is dissolved, and salt is dissolved, and mixing mechanically spreads fat, which will have an effect on the development of gluten. Now, the entrapping of air in the dough to create gas nuclei turns out to be really important. I'd like you all to just imagine in your minds that you have in one hand you're holding a large balloon, and in the other hand you're holding a small balloon. They're both made of exactly the same material. The only difference in the balloons is the size. You can try this experiment at home, get 2 balloons and blow them up. And you will find that it is very much harder to get the smaller balloon blown up than it is to blow up the large balloon, even though they're both made of exactly the same material. And the reason that it's harder is because it turns out that creating a bubble, which a balloon is, or a gas nucleus is in dough, requires one to overcome resistance to expansion. And the resistance to expansion mathematically is equal to the surface tension of the material times 2 divided by the radius. So the part about divided by the radius is critically important here. As the radius gets smaller and smaller, then the resistance to expansion gets larger and larger. And as the radius approaches 0, the resistance to expansion increases to approach infinity. So that if there were no gas nuclei to start with, they wouldn't be created by the yeast in its fermentation process. And mixing creates the gas nuclei that can be expanded during the leavening process. So other comments about the mixing process. Oxygen gets consumed almost immediately. It is grabbed and used by yeast and other living cells that might be in the dough, and it's used up by the time the mixing process is finished. Nitrogen is poorly soluble in water, and it stays pretty much in the gas nuclei that were formed in the mixing process. Carbon dioxide that's created during the mixing process diffuses into the gas nuclei. The size of the gas nuclei depend on a lot of factors, including the atmosphere, the mixer speed, shear forces, and the like. So as we've talked about, mixing exposes the components of dough to oxygen. And oxygen, through its ability to oxidize other substances, can change weak bonds that are formed by sulfur and hydrogen into very strong bonds that are formed by two sulfur molecules coming together. Oxygen in a dose strengthener like ascorbic acid can provide this same effect. As I mentioned earlier, the deleterious effect for bakers is that oxygen can oxidize carotenoid pigments, change their properties, and by changing their properties, change the flavor that they would otherwise add to the dough. During mixing, water is absorbed minimally by starch. As Andrew mentioned, the damaged starch particles can take up some water slowly, but during mixing, it's a minimal amount of water that is taken up. Water is taken up maximally by proteins during mixing. When the water seems to disappear into the flour, it's actually in the mixing process. It's going into the protein that is in the flour. So we'll go back on camera, and I have a visual for you for this.
So actually the protein is absorbing, I guess it absorbs like twice its own weight in water in the dough. And if you're thinking about baking whole grain products, whole wheat products, whole rye and things like that, the other major component that's absorbing water in that system is the fiber. And so we won't go into the chemical details of the fiber, but it's for us indigestible polymer of sugars, unlike the digestibility of starch. And they suck up water like a herd of thirsty camels. And so if you've got, and that's one of the reasons why if you go from a formulation that's done for a refined flour, just a straight baker's flour, and then want to reformulate to a whole wheat, that you have to up the water because you have to compensate for the absorption of the fiber.
Camera? Yep. Wrong camera? Okay, so could you hold these, please? And this is going to be a two-person video now because I need a little help. But imagine here is a protein. It's a spiral-shaped protein, and now it's in a water environment. Here comes a water molecule that inserts itself into the protein. It's weakly held there by electrical bonds, and I can't hold any more than these two, but you get the idea. This is how proteins entrap water, and this is where water that's not going into the fibers that Andrew mentioned, this is where the water goes during mixing.
In fact, amongst the starch, the protein, and the fiber in there, there's a fight to the death over the water. They're all very competitive over it.
So during mixing, gluten development begins. Air is entrapped in the developing matrix, as we mentioned. Starch is entrapped in the gluten matrix. And dough cohesiveness begins to occur. There's dough cohesion and dough adhesion. By cohesion, I mean the integral properties of the dough, which causes it to be a single mass, versus adhesion, which is what causes the dough to stick to the mixing bowl or the baker's bench. So cohesion it continues to increase as the gluten development progresses. So water absorption increases with mixing intensity, as the mixing intensity increases, the shear forces and elongation forces that are involved distribute and resize the gas nuclei. There are some stages of mixing. Stage 1, is a short dough is formed. In the middle of mixing, stage 2, cohesion starts to increase. By stage 3, there's very strong cohesion. It's the mixing bowl is walls are cleaned by the dough. It's possible to draw a window from the dough. And stage 4, over mixing, there's a sticky, extensible, soft dough that has resulted. So as on the effects of mixing on the final product, coherence, as we mentioned, increases. Crumb softness and resiliency increases because of that. And the crust that will be formed in the baking process toughens. Temperature definitely affects fermentation. For every 1 degree centigrade, or approximately 2 degrees Fahrenheit, there's a 10% change in the rate of fermentation at normal room temperatures. I'm not talking about the extremes of temperature, but just at the temperature that bakers usually work. A couple of degrees Fahrenheit will have a significant change on the rate of fermentation. And that knowledge can be used very helpfully in the manufacture of breads. I made a note there that 8 grams of ice per kilogram of dough will drop the temperature 1 degree centigrade and thereby drop the fermentation rate about 10%. Next slide, please.
So in the world of flour testing, there are a whole bunch of different ways of looking at the mixing process. Now, the example that I have on the screen here is a little machine called a mixograph, but there are a whole family of O-graphs. There's the mixograph, and there's the one that you're probably more familiar with, if you're familiar at all, which is the farinograph, but also then associated with another test that we'll get to later, which is really looking at dough strength. There's a mixolab, which is made by the Chopin labs. But in general, they're called recording dough mixers, and they all basically have a similar kind of principle behind them. So right now I'm just going to base this on the mixograph. There's in the playlist that you have, there's a nice video from the Canadian International Grains Institute, I think that's who it is, that goes through the process of the farinograph, but it takes about 7 minutes, and I think that we will, in the interest of time, not try to show that concurrently with this presentation. So I'm going to move the cursor around on the screen here for a little bit. So the mixograph was developed in like the 1930s and hasn't really changed much, except we can whack a computer on it now, but I still use the paper traces because they're easier to read. So if we look at the red curve, the early part of this curve is describing this, when it's, you would see in the mixer bowl that this is when the dough's coming together, and it's going from a shaggy mass into something that looks a little bit more coherent. And so about here, if we were going to rely on folding, that this one might be where we'd stop a short mix. A modified mix or an intermediate mix might stop about here on this particular curve, and an intensive mix would stop just past this peak of full development. And I'm guessing that most of you have mixed doughs by hand, and you would have felt the change in stiffness or consistency of the dough as you go from the shaggy mass through the different stages of development. And so, but this is just a way of mechanically measuring it. Now, the difference here is if you look at the panel at the bottom, that you can see that just using the same instrument going from left to right, I get quite different responses from the flour to the same mixing process. And so if you have the opportunity to mix in your own place with a variety of different flours, you will already know that to get to, for example, an optimum type of short mix or intermediate mix, that it actually can take different lengths of time depending on the source of the flour that you were using. So in general, the weaker the dough, to a certain extent, the shorter the time is going to be to get to optimum development. But we can make some sort of inference about the performance of the dough by looking at these recording dough mixes. In the farina graph, you'll see, you know, and some of these will show up on standards of identity. You might, for example, specify a range of stability times. So the stability is this parameter here, the length of time that the dough stays in a fairly stiff and unbroken down circumstance. Sorry, I just can't find the right word there. You really don't want to get out here into well over-mixed. I imagine most of us have never seen that. If we keep mixing something in the mixer graph, which is incredibly aggressive little mixer, even though it only holds like 1/3 of an ounce of flour, you can stretch it like, you can stretch the dough like honey, and it's quite sticky and unworkable. If you look at the bottom right panel, you'll be able to see this is directly from the King Arthur flour website, some of their specifications for some of their flours, and you can see that they actually do look at the absorption from the farina graph. So this is the amount of water that it takes to get to this magical 500 line. The units are completely arbitrary. They were invented by Brabender in the, I don't know, the 1930s or 1940s, based on the hand feel of a specific baker in Germany, or so the story goes. And but you will see that they do have specifications about how long it takes to get to the peak, how long the stability is, and as you can see as you go, just to compare the Sir Lancelot high gluten to the Sir Galahad hard winter, that you can see that the hard winter wheat, which would probably be a more balanced wheat for craft baking, that the water absorption is lower. The peak time is about the same, but you can see that there's a slightly lower stability in terms of the mixing tolerance of the hard red winter wheat. To try and show that in a kind of an extreme way, if you go and look at the pastry flour, which shouldn't have much dough strength at all, milled from a soft wheat, soft wheat, low starch damage, very low water absorption, very short peak and very short stability. So very, very different types, but you can get some kind of inference for your dough performance by looking at these specifications and understanding where they come from in terms of these recording dough mixes. And they're really, really useful. And I would suggest, you know, when you have the leisure time to do it, look at the link that we've provided that will show the procedure and the interpretation of the farina graph. And so some of the other flour tests that we can do to measure absorption, there's a thing called the solvent retention capacity. So solvents are basically either water or different solutions. And really, I'm just going to think about water right now. You just basically wet the flour up and hydrate it in water for about 20 minutes, spin it down at a prescribed speed in a centrifuge and measure how much water that the flour has absorbed. And one of the things that's always drives bakers mad is if we keep getting, you know, really wide variations in absorption from one batch of flour to the next, and, you know, we don't really like dealing with that at 3 o'clock in the morning. So, you know, the flour millers, if they have the opportunity to blend to try and at least stabilize the absorption from one batch to another, this is the sort of tools that they could use. The other thing that we can do, so we've mentioned issues to do with mixing, but there are also ways of measuring things that you would feel on the bench now that when you have for example, when you first go into pre-shaping, and certainly when you go into shaping, in terms of how far the dough will stretch without tearing and how easy it is to stretch the dough out. And so this particular test that's on the screen now is called an extensograph test. So the dough is mixed in a farina graph to a prescribed condition, which is the optimum or the intensive mix, and it's stretched with a hook and the cradle is on a pivot, and so you can measure the force that's required to stretch the dough, and you can measure how far the dough needs to be stretched before it tears. And you've done this with your hands. You know, when you go to do stretches and folds and you stretch the dough out, you know that some doughs are harder to stretch than others, so this is the resistance to extension, and that some doughs will just naturally stretch out a lot further than others before they tear. And so you've felt this yourself. The other way of looking at dough strength, which is probably maybe more familiar to craft bakers, is the Alvear graph. And in this circumstance, once again, you take a fully developed dough that's been pre-shaped, and then you blow a bubble in it. And a bubble, according to the company Chopin, is more appropriate because, in fact, we blow bubbles in dough to make bread. And there are a number of things that you can get from this bubble that are related to how far you can stretch it and how tough it is to stretch. And there's a, pretty sure I put a link to an Alvear graph on the playlist, but I'll double check that. And so sometimes if you look at Alvear graph specifications, you will see these parameters P, which is the pressure, W, which is the area, which is the work, and L, which is the length. And other than the work, these are the P and the L are analogous to resistance to extension for pressure and extensibility, which is L. And you can make some inference about the performance of the dough from looking at Alvear graph data. So, for example, if you are buying flour from Heartland Mills in Kansas, they actually will provide you with the Alvear graph specs on the flour batch that you're buying from them. And it's worthwhile maybe having this as a reference, for example, if you're looking at Alvear graph data to understand what it means to you.